right, well, as we get started with the second semester, we've really wrapped up most of the non-graphing concepts that you need to know for algebra. So we're going to spend this next quarter really focused on graphing concepts. So you'll need graph paper really the rest of the quarter. There'll be a day or two here or there where you won't use graph paper, and then you'll get right back to using it. So how many of you have a spiral notebook with graph paper in it? How many have loose graph paper maybe in a binder that you can bring? Okay, so make sure you have it with you. If you're watching on YouTube, don't have graph paper right now, pause video, get some, because you're going to have a really hard time keeping up. I will say I'd recommend you keep your notes in the same notebook you've been using, unless, of course, you're starting a brand new notebook for the semester anyway, which is what I have to do because I used up my notebook last semester. But keeping your notes together I think will still help you, but you'll want the graph paper for your graphing. Obviously, graphing is something we talked about quite a bit in Algebra 1, but for a few of you, that's been a couple years. So for some of you, that was last year. So some of you might remember things a little bit better than others. Going back to graphing, obviously, you have graph paper. I have a little graph grid thingy that puts graph markings on the chalkboard. In and of itself, a bunch of little squares isn't really very useful for graphing unless you give value to the squares. And the way that we'll give value to the squares is by drawing something we've seen quite a bit lately, well, before Christmas, and that's a number line. But not one number line, but those who remember graphing know we use two number lines, and we'll cross them at right angles to each other, or perpendicular to each other. And these two number lines have names. Anyone remember what we call these number lines? Abby?
X and Y.
That's how we label them, but they're called? Well, the plural is axes. One axis, two axes. Okay, so if you'll write that term in your notes, these two number lines are called axes. This is the x-axis, and this is the y-axis. Okay, so singular is axis, plural is axes. And when you draw these two number lines on the graph paper, now you have something that can actually allow you to do graphing. Now we have something called the Cartesian plane, also called the coordinate plane. Plane simply refers to a flat surface, so we're graphing flat things. Okay, we're not graphing 3 dimensions on graph paper, though that's something that you will learn later is how to simulate a 3-dimensional graph on graph paper. But we're just doing 2-dimensional graphing here. It's a Cartesian plane. Plane just means flat surface. Cartesian's named after a mathematician, René Descartes, who actually came up with this graphing metric, and his work ended up laying the foundation for calculus to come later. Again, sometimes this is called the coordinate plane. So depending on the math classes you take in the future, you may hear coordinate plane. What's that? Same thing as a Cartesian plane. But simply uses an x-axis and the y-axis acting at right angles to each other. Now, this point where they intersect is the zero of both number lines. So this is 0 vertically, so starting at 0 and it goes up to positive infinity. Starts at 0, goes down to negative infinity. Starts at 0 forward to infinity, we're very used to that, and then 0 backward to negative infinity. So they're just number lines. This particular point here that is the 0 of the x and the 0 of the y-axis is called, anyone remember? It's also the 0 of any number line. The origin. The origin. Origin simply means beginning. So it's the beginning, if you will, of how and where we'll plot points. We'll start at the origin to go from there as we graph. This Cartesian plane, this coordinate plane then, because there are two crisscrossing perpendicular axes, is formed into 4 sections. These sections are referred to as quadrants. Quadrants. Those of you who've already had geometry will remember a quadrant is also a fourth of a circle. But of course, if we were to put the compass here and draw a circle, we would have a circle divided into quadrants. Okay, so the term is not misused in either case here. But quadrants, it's important to note what quadrants are which. We'll actually start not here. Like if we were reading, we would kind of read this way. So we would assume this is where we begin. But this quadrant is actually quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So the Cartesian plane has these 4 quadrants. Quadrant just means a 4th section. And if you want to remember it, if you think of the letter C, would start here, and you work your way around, at least if you're drawing it correctly, right? Some people might draw it backwards, but if you're drawing correctly, you start C there, and work your way around. So if you want to think Cartesian or coordinate, they both start with the letter C. Maybe help remember starting there in quadrant 1 and going around. Now on the number lines, I am way too lazy starting at 0, right? 1, 2, 3, 4, 5, 6, 7. I am not going to number my number line that way. I'm too lazy. Some people will number every 2, so they'll put all the even numbers. They'll start with 0 and then go 2, 4, 6, 8, and so forth. I'm too lazy even for that. But like if I did like every 7, okay, that would be really hard to tell what's what. I've kind of found the perfect number for maximum laziness in both labeling and reading a Cartesian plane is the number 3. Because any number is either right before or after or on a 3. Right? So 2 would be right before, 4 would be after, 5 would be before the 6. So what I'll do is I'll start here with 0, and I'm not going to write it, but this is 1, 2, 3. Then 4, 5, 6, 7, 8, 9, 12, and going backwards, you got, of course, your negatives, -3, -6, -9, just like a normal number line, right? You got all your increments on there. And then vertically, we'll start at 0, and we'll count up, but we're going to stay to the left-hand side of the y-axis. So we'll go up 1, 2, 3, 4, 5, 6, 9 kind of there at the top, and then coming down -3, -6, -9. We want to keep the first quadrant clear. So we put our labels below the x-axis and to the left-hand side of the y-axis so that my first quadrant is empty. That's where most of my graphing will normally take place. We want to try to keep that clear of any increments. But every Cartesian plane that we do that's graded for a quiz or test, and therefore every Cartesian plane that you use for homework should have arrows at the ends of the axes showing that it extends to infinity, x-axis and y-axis labels showing this is Cartesian graphing, and increments. Now if you want to label every single number, more power to you. I'm an every 3 guy myself. But this is how we'll set up our Cartesian planes. Again, those who've had me before, this should start to sound familiar, like, oh yeah, I remember this. Audrey's kind of like, no. All right. And then you all should have also be familiar with graphing from years past, somewhat at least. Okay. All right. Now with graphing, every single point or dot that you could make on this has a particular value. For instance, if I were to plot this point right here, well, it lines up right here with the 8 on the x-axis. So its x value is 8. But it also lines up to a particular y value. Its particular y value is -3. Now, if I just said I need an x value of 8, any one of these points could work, correct? If I just said a y value of -3, well, any of these points all are down 3 or have a y value of -3. But you get an exact location when you put the x value listed first, comma, y value listed second, and we'll enclose it in parentheses. Now you say that almost looks like a range of values for an inequality, right? 8 to -3, well, that would be backwards for one thing. It depends on context. It does look just like an open-ended interval, an open-bounded interval between 8 and -3. Obviously here we aren't working with an inequality, so we know the notation refers to a particular point. This x value, which is always listed first, is called the abscissa of the point. The abscissa of that point is 8. Notice the spelling, there's a silent C in there, so it looks like abscissa, but we don't want to give anyone ideas, so we say abscissa. The y value also has a name. It's referred to as the ordinate. And the ordinate is always listed second. So the abscissa listed first, the ordinate listed second. And when I put them together like this to give an exact location on the Cartesian plane, we have what are called the coordinates of the point. You might recall this from Algebra 1, that co means with. So when you put the abscissa with the ordinate, you have the coordinates, or the exact location of the point. Again, all of this should be reviewed for you, but for some of us, it's been a little while since we've learned these terms. Also, a lot more terms right off the bat than we're used to in a math class. Right? We're used to in math class processes, aren't we? Here's the problem. What's the process I use to solve it? Let me memorize it, learn it, and be able to execute it. Well, now, a whole bunch of terms. So you can imagine that upcoming quizzes, upcoming tests will have a lot more terms on them than we're used to. So make sure you spend some time studying. For those who had geometry, think geometry class. For those who haven't, You'll find out about geometry class. Kendall's having flashbacks. Her face looks panic-stricken. It's not quite as bad as geometry as far as a lot of memorized terms. But anyway, how do we plot a point then? If I, for instance, said I want to plot the point -3, 4. Well, we would start at the origin. We start at the beginning, and the x value is listed first. Well, x, remember, is horizontal. So horizontally, I will go -3. Well, negative means going backwards. And then vertically, I'll go +4. Well, positive refers to upward. And this point here in the second quadrant is the point -3, 4. Easy enough to plot a point. If I had the point -7, -1, how would I plot that point? How would I find that location, Michael?
Go left 7 and down 1.
Starting at the origin. Good. So you said go left
7
and then
down 1.
There we go. And there it is in the third quadrant. -7, -1. If I had the point 2, 2, how would I locate that point, Maddie?
Go to the right 2 and left.
Starting with the origin, right 2, up 2. There it is in the first quadrant. Notice the first quadrant only has positive x's, positive y's. Everything in the first quadrant is positive. Well, we like positive numbers best, don't we? Negatives mess things up. So that's why a lot of our graphing takes place in the first quadrant, because we prefer to use positives if we have the choice. Notice in the second quadrant, all of the x's, the abscissas, will be negative. The ordinates, or y values, will all be positive. Everything's negative in the third quadrant. Always negative. Any of you feel like a third quadrant person? Always negative? World's always about to end. Life is terrible. How many more first quadrant people? Everything's happiness and rainbows and sunny skies. How many are like kind of like quadrants 2 or 4, a little mixture of both? You're more level-headed than that? Yeah, I would. No, you lose some. You lose some. I'm a third quadrant guy. What can I say? Comes from being a Notre Dame fan. Anyway, I really thought this was our year to finally win a bowl game. We had a 21-point lead and found a way to blow it in the last minute. Anyway, I'm not going into that. Questions on plotting points. How many say, I remember plotting points, I got this. I could plot a point if you gave it to me. How many say, I don't remember anything about plotting points and I don't even understand them? How many are somewhere in between? How many are too lazy to raise your hand? I get a little head nod from Michael. Okay, whatever, raise his hand for that. All right, I want you to set up a Cartesian plane on your graph paper now. Go and get a graph paper, set up a Cartesian plane, an x-axis, a y-axis. You don't necessarily need to label quadrant numbers, though if you wanted to, it might help you remember which quadrants are which, particularly if this is something you don't remember from Algebra 1. Get your increments on there. Again, you don't have to do every 3. I wouldn't do much more than 3 or 4 as far as skipping every so often, but get something on there you're comfortable with. Remember, the origin counts as 0, not as 1. I've seen students, if you look up this way real quick, I've seen students do this. They'll be like, okay, 1, 2, 3, 4, 5, 6. No, this isn't 1. This is 0. 0, 1, 2, 3, 4, 5, 6, and so forth. So just remember that as you're labeling. Go get your Cartesian plane set up. Let me zoom in just a little bit for our YouTube viewers. Genesis missing you today, so hopefully you'll be back with us tomorrow. If I wanted to label a point, oftentimes, even in geometry, points are indicated by capital letters. So for instance, if I wanted to call this point, I don't know, let's just say G. If I want to call this point, let's just say N. If I want to call this point something random like H. Okay? Well, I would label -3, 4. I would put the capital G next to the point. If this point were N, I would put the capital N next to the point to label it, or the H next to that point. Does that make sense? Okay, so I'm going to give you, let's see, 8 points to plot on your Cartesian plane. And let's go with A. Your first point will be the point 2, 4. Let's say that B is the point -3, 2. C is the point 1, -2. D will be -3, -4. E will be 0, 6. F will be -5, 0. G will be 7, 3, which means I need to erase my last G. And H, I will also need to erase my previous H, -6, 7. So go ahead and plot all of those points on your Cartesian plane. Move the lectern out of the way for you a little bit there. Yeah, Abby whiplash. It's like, I hate this corner. Who was there before? Michael? Got to afflict one of you. Dad asks, how's class going? Well, as long as I keep one of them in the corner, we're okay. Last quarter, I had to have both of you in the corner. Abby's got her 8 points plotted. Kendall has hers done. Brandon is finished. Gavin is finished. Audrey. Maddie. And Michael. All right, let's go ahead and see how we did plotting these points. A should have been in which quadrant class? First quadrant. Forward 2 and up 4 is where our A should have been. Point B should be in which quadrant? Second quadrant. We're going to go backward 3 and upward 2. Point C. Fourth quadrant. We're going to go forward 1, downward 2, so just barely here into the fourth quadrant. D, third quadrant. Backward 3, downward 4. Letter E. Isn't going to be in a quadrant at all, is it? Where's it going to end up? On the y-axis up here at 6. Again, over nothing, up 6. So E there on the y-axis. F. X-axis, we'll go backward 5 and then up and down, nothing. So we just stay right here on the negative x-axis here at F. Letter G. First quadrant again. We'll go forward 7, upward 3. And then H is in the second quadrant again. We'll go backward 6 and then upward 7. Would be right here. And there's my point H. How many had all 8 points in the exact same locations? Again, the x values, class, are referred to as the abscissas, and then the y values are called the ordinates. The location of a point is called the point's coordinates. Coordinates. Good. Now, one of the things we did with our graphing in Algebra 1 was we would graph lines a lot of times. In fact, I think that's all we graphed in Algebra 1, if I'm not mistaken. We never got to the other stuff in Algebra 1. Maybe you did, so some, maybe getting past lines, when we get to some other graphs later on this semester, you'll say, oh yeah, I remember doing that. But for those who had me in Algebra 1, straight lines was as far as we got. And equations that generate straight lines are called linear equations. Linear equations. If you go and write that term in your notes, we see that root word line R. AR means like pertaining to, line, like or pertaining to lines. Okay? Linear equations, you need to know, they always graph as straight lines. A little slip into geometry there, sorry about that. How you'll identify a linear equation? Well, the linear equation needs both an x and a y, because these equations that we'll graph on the Cartesian plane have both x and y values, but both will be to the first power. X and y to the first power only. So a linear equation will have both x and y in it. You could call it a literal equation then, because there's an extra letter beyond what we're used to, but they'll only be to the first power. One of the things then that we spent quite a bit of time doing in Algebra 1 was graphing these linear equations. And there's 3 ways in which we can graph, or by which we can graph linear equations. So underneath this, kind of a sub-point, if you will, graphing linear equations. Graphing linear equations. free methods. So I'm going to go Roman numeral 1, and then later on Roman numerals 2 and 3. The first method that we talked about in Algebra 1 was graphing by what we call the table method. We would set up a table and use that table of values to graph. This is an effective method if you see an equation you're not sure how to graph. Table method always works. Figure out some x's and y's and plot them. So a quick refresher on how to use the table method, though we won't use it often. First of all, you'd want to set your linear equation equal to either x or y. Meaning you want to get the x or the y by itself. For instance, if I had the equation 2y minus x equals 2. Well, that's a linear equation. I've got both x and y to the first power. But if I wanted to graph the linear equation, I need to get a letter by itself. Audrey, which letter would you like to get by itself?
Okay.
The x? How would you do that?
Can I change my mind?
Okay, sure. You want to go with the y?
Yeah.
How would you do that?
You move the x over.
Okay, to get 2y equals x plus 2. All right, and then what would you do to get the y by itself?
Divide the 2 away.
Divide the 2 away from both sides. Now, I'll be honest, I actually liked your first choice. I actually liked the x better, because see, when the y, you get this ugly fraction, but you know what? It's okay, we're going to roll with it. The point is get a letter by itself. That's all that really matters. All right, step number 2 is to set up an xy table. It's a basic T-chart, 2 columns. It is important to make sure you put x's then y's, so that you get your sets of coordinates listed out with abscissa before ordinate. So xy table. Step number 3, plug in values for the independent variable. Have we talked about the independent variable this year? I feel like we have. We had constants, which are numbers. Dependent variable is the one that's by itself, remember? So here, y is the dependent variable, and then x would be the independent variable. So plug in values for the independent variable. So we think of some random, easy, numbers to plug in for x. What's a nice, easy number we might plug in for x, class? 0. What's another number we might plug in for x? 1. Maybe another number? 2. Easy, right? So then we actually plug them in. 0 goes in for x. Well, 0 plus 2, class, divided by 2? Plug in a 1. 1 plus 2, divided by 2? 1.5. Now we might say, ooh, I didn't really like fractions. Let's forget that one. All right, let's plug in a 2. 2 plus 2, 4 divided by 2? 2. That's a nice, easy point. Let's think of another number we could plug in that'd be nice and easy.
4.
4. All right, 4 plus 2, divided by 2. Is there anything wrong with 1, 1.5? Not really. I just don't like fractions. I like nice, easy, well-defined points. Now, you will want to do this. Get 3 points. So I stopped once we had 3 nice, easy points to use. Why 3? Those who were in geometry last year know that how many points determine a straight line? 2. 2 points determine a straight line. Oh no. 1 point you can draw an infinite number of lines through, correct? Just draw a point, you can do a whole bunch of different lines through that. 2 points, you can only draw 1 line. So why 3 points? Just as a check, right? If all 3 points line up, you know you did it right. If the 3 points form a triangle, you're not sure which 2 points are right and which point is wrong. So maybe do a 4th point, like, oh, those 3 line up, that one's the weird one, that must be wrong. But that's why I recommend 3 points. That way if you accidentally screw one up, you have a way of checking yourself. Okay, and from here, plot the points and connect the dots. One thing you're going to find to be helpful is a straight edge of some kind, maybe a ruler or the underside of a protractor, something like that. You can also take a sheet of paper and fold it over a few times to get a nice straight edge, but you'll find that to be very helpful as we graph in this section. You've already got your Cartesian plane set up. I suppose you could try to use it again, or maybe set up another Cartesian plane. Oh, there were some push pins in the way. Oops. I used to have those up there, but this class I have them for hanging posters something. All right, so again, if you want to draw a new Cartesian plane, you can. If you just want to roll with the one you've already got on your paper, by all means, do so. And zoom in just a little bit here, make it a little easier for Genesis to see. And if you're setting up a new Cartesian plane, your y-axis, your x-axis, make sure you put arrowheads going to infinity and negative infinity. Make sure we label x and y. By the way, the x and y labels only need to go on the positive ends of the axes. We don't have to label the negative ends. You can. I'm lazy. Why would I do more work than I have to? And of course, I'll label every 3 units on my slightly sagging x-axis and on my y-axis. Kind of like whoever tried to fix my fireplace earlier. Anyway, all right, so we plot our points. Our first point is the point 0, 1. So class, we go over nothing and up 1. Then, starting from the origin, we go over 2 and up 2. Then, starting at the origin, we go over 4 and up 3. Hearing a weird whisper from somebody there. And then again, if you have a straight edge, it's very handy. I happen to have this rather chalk-covered, less chalk-covered now, straight edge. If you don't have a straight edge, well, this thing that hurts on me, this is solid metal.
Demonstration.
Why, sure. Funny you should suggest it, Michael. All right.
Brandon.
Brandon is closer. It's true. Can I reach? I can. Just kidding. All right, just kidding. I hit myself instead. That wasn't good. All right. Abby suddenly doesn't mind the back. All right. Why am I always behind Brandon? It's to protect you, okay? Don't knock it.
You're welcome.
All right. And we get our nice straight line there. Some people will say you got to put arrowheads because technically this line goes to infinity as well. I'm lazy. I don't usually draw those arrowheads, but mathematically probably ought to. And there's our linear equation, our straight line. And we graphed it using the table method. Now that we've done it, how many would say, oh yeah, I remember doing this back in Algebra 1, setting up the XY table. Let me give you an equation now. I want you to do this at your seats. You can use the same grapher, especially if you just set up a new one. If you're using the old one and it's just too cluttered, maybe go and set up another one. 6x negative 2y equals 4. One thought on this equation, I could make my life easier and not have to deal with so many numbers if I do what class?
Factor 2.
Divided 2 out of everything. So if you just knock that 2 out of everything, it's going to make your life a little easier. Go ahead and graph this equation using the table method. And in case Gavin and Genesis and Brecken, you can't read the shirt because he keeps moving. It says, I see you have graph paper. You must be plotting something. So anyway, corny math joke. But I think I got this for a birthday present. I think somebody, probably my wife, wanted to give me corny math stuff. Aided my nerddom. Yeah, she bemoans marrying a nerd, but then she goes and enables it. This is where, by the way, if you have different colors of ink, that kind of thing, it can be really nice for making different colors. I do have different colors of chalk. I just didn't think to bring the extra colors down here, so I used a dotted line to show the difference here. How many got a line that looks like this? A line that looks like this. Now again, the way I did it, of course, I knocked the 2 out as I recommended, and then here's where I wanted Audrey to do this last time when she said she was going to get this particular line. I think it was an X last time, but just a double switch. Right? So the Y over is the positive, bring the 2 over as the negative. So since the Y is by itself, I'm plugging in for the X. 0, 1, and 2 are my numbers. I got these. I suppose had we decided to go 3x equals 2 plus y and then divide away the 3, then in that case, we'd have been plugging in values class for the y. And I probably don't want to plug in a 0, because 2 plus 0 is 2 divided by 3 is 2/3 for the x. And that's pretty awful looking, right? But maybe a 1, I can plug in a 1 and get what? 1. If I plug in a, not a 2, 3, 4, plug in a 4, I get what? Somebody died. It's okay. 2. A 7, I guess I've got room to plot. I could do a 7. 7 plus 2 is 9 divided by 3? 3. And those points would be in the same points, right? 1, 1 is already here, 2, 4 is already here, and then 3, 7 would also be on that same line. So you could have gotten the same line that way as well. Questions on the table method of graphing. But this method was something we didn't stay with very long when we graphed linear equations because it takes a little while and slow and painful and generally not favorite. Okay, so we went to another method last year in Algebra 1, or a couple years ago in Algebra 1, as the case may be. It was what we called the Intercept Method, or graphing using intercepts. Intercepts. There's a term we need to get in our notes and know what it means. Intercepts refer to points where a graph crosses the axes. Points where a graph crosses the axes. Points where the graph crosses the axes. For instance, if we look at the last line I just drew, there's an axis crossing here and here. These points are my intercepts. This is called the x-intercept because it crosses the x-axis, and this is the y-intercept because it crosses the y-axis. Here's my y-intercept, and then down here is my x-intercept. Make sense? All right, so intercepts. Well, what's the key to an intercept? Well, this value is you go over 2/3, it looks like, and then up and down 0. This intercept, you go over nothing, just down. So here, the up and down is 0. Here, the over, the side to side is 0. Intercepts always have zeros. So your key then is to set each variable equal to 0. Set each variable equal to 0. For instance, if I have the equation 5x negative 2y equals 10. Well, what I'm going to do is I'm going to set each variable equal to 0. First, I'm going to put a 0 in for the x, and the next time I'm going to put a 0 in for the y. Well, if I plug a 0 in for the x, this whole term falls out, and I'm left with negative 2y equals 10. What must y equal, class?
Negative 5.
Negative 5 when I divide away the negative 2. But if I plug a 0 in for the y, this term drops out. I'm left with 5x equals 10. So x must be 2. And those are my two intercepts. 0, negative 5, over nothing, down 5. And 2, 0, over 2, up and down nothing. Now here, I'm going to use the fact that 2 points determine a straight line. And I'm going to just go off those 2 points. Why am I okay with just 2 points here? Well, because when you're plugging in zeros, it's really unlikely that you're going to screw that up. I mean, you made it this far for a reason, okay? Surely you can plug in 0 correctly and not screw it up, right? So 2 points is probably sufficient, and there's our line with just 2 points, and they're easy points. So this, to me, is a much preferred method over the table method. Would y'all agree? All right, so we set each variable equal to 0. Plot both and draw the line. Oh, that's right. This isn't geometry. Line. It pains me. It really pains me. All right, plot both, draw line. Easy enough? How many remember the intercept method from Algebra 1? You say, yeah, I remember plugging in the zeros. All right, some of you maybe not as much. Give this one a try if you would. Y minus 2 equals 3x. Y minus 2 equals 3x. Using just the two intercepts, plugging in zeros, remember, go ahead and figure out what those points are, plot them, connect the dots to graph that linear equation. First class, we'll plug a 0 in for x. If I plug a 0 in where the x is, this becomes y minus 2 equals nothing. What must y equal as we bring the negative 2 over, class? Positive 2. And then for the other intercept, we're going to plug a 0 in for the y. Well, we plug a 0 in for the y. What do we get for our x-intercept? Negative 2/3. Well, here we go. All right, so 0, 2, no problem. Over nothing, up 2. And negative 2/3 is 0. So you're going to go backward, your best estimate, 2/3, right? And up and down, nothing. And when you connect the dots, you should get a line not quite parallel to the last one, but not terribly different either. How many got a line like that for this equation? Are there any questions on how to use the intercept method? Now here we see one of the shortcomings, right? You may end up with fractional intercepts, and that's a bit unfortunate. There is an even better way, and this was the main way we used last year, the main way we will use this year, method number 3. And it's slope-intercept form. Graphing using slope-intercept form. However, we're not going to be able to get to it today because there's some things we need to talk about before we can get to using this method of graphing. How many of you remember the term, at least, from Algebra 1 slope-intercept form? All right, so let's review some other things, though, that we need to understand before we can get to slope-intercept form. So we're going to pause in our notes, maybe leave a space, and let's pick up some other notes. First of all, what is slope? We need to understand slope before we can talk about this slope-intercept form. Slope refers to the slant of a line. The slant of a line. Obviously, we've got these two lines that have very similar slant. We had another line earlier that slanted like that. Somehow, I'm not sure how, we didn't end up with any lines that slant like that. But there's a lot of different angles of slant that you could have. Well, slope is defined, although it can be thought of as the slant of a line, it's defined as rise over run. Something that should sound familiar to you, right? Rise over run. Well, when I say rise, if I were to say, class, would you please rise? What would you do? You'd get up, right? Rising always refers to going up. If my students are out on the PE field and we're standing in the middle of the PE field, I say, run! Now, usually they know what that means. It means run a lap, and we always run a lap a particular direction. I think maybe once or twice I was feeling weird and I made them run the other way. It was just too strange. Run, well, you could run a lot of different directions, right? And running doesn't refer to going up, right? Like, that'd be very strange if I could run up the wall, right? Running refers to moving horizontally, moving in the X. So run could be along the X, either forward or backward. Forward run is positive. Backward run is negative. So a line that goes up and forward has positive rise over run. A line that goes up and backward has negative rise over run. Now, think about rise. Rise is vertical, correct? Y is vertical. So rise can be thought of as a change in the Y for a line. Run could be thought of as horizontal, the change in X. for a line. Are you familiar with this delta symbol meaning change? Is that something you've seen in your science classes? Delta simply refers to change. So this means change in y over change in x. That's the mathy way of showing slope. But it's simply rise over run. Mathematically shown, delta y over delta x. Anyone remember, by the way, the letter we use for slope? M. Why? I don't know. But to M, like slope. Slope. M. I don't know. Anyway, so this is actually our equation if you want to take the whole thing, including the letter M. M equals delta y over delta x. Change in y over change in x. So for instance, for this line here, well, if I were to track this point to this point, which it looks like we just missed, well, there's a certain change upward, a certain rise that the line has, and a certain run that it has. It appears to rise 5 and run 2. So we'd say the slope of this line is 5 to 2. If I were to go with this line that I drew rather haphazardly, there's a nice neat point, there's a nice neat point. Well, it appears to rise 3, and it runs backward 4. Rise 3, run backward 4, we'd say negative 3/4. 3 over negative 4, but we slide the negative to the front of the slope. Does that make sense? Anyone remember rise over run, change in y over change in x, all that kind of thing? All right. Well, for homework this evening, you're going to work on some things that have nothing to do with what we talked about. It's just going to be some review over some basic things from last semester. Page 168, I have just 4 problems for you to do. Very light assignment here tonight. Page 168, I want you to do the review 1 through 7 odd. Page 168, the review 1 through 7 odd. Again, no homework over this stuff, but I am going to strongly encourage you study your notes tonight. Study your notes so you don't fall behind on graphing. A lot of terms to keep up with, so make sure you're keeping up with those. All right, have a wonderful rest of your day, and you are dismissed.